Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back, dear students. In the last two lectures, I talked about the balanced faults, and we also solved a problem in order to get more clear understanding of the concepts. So today we will start with the unbalanced fault analysis, and I will be mostly talking about the symmetrical components. So even before starting today's lecture, let me quickly revise the contents of the last two lectures. We discussed the fault in general, that when a fault can appear in a power system due to various reasons. And I mentioned that fault refer to a condition when the parameters of the system exceed the allowable limit. So that basically is characterized as a faulty condition, whether it's a current or it's a voltage or it's a frequency. So whenever these parameters exceeds the allowable limit or exceeds the standard operating limits, then that condition is characterized as a fault, and steps need to be taken for clearing the fault as soon as possible in order to avoid damages. So we discussed that fault could be of different types. Could be a balanced fault where all the three phases are equally affected, or could be an unbalanced fault. So we discussed the balance faults, and we also discussed the analysis of the balance fault using Thevenin theorem. So we discussed that the analysis of the balance fault, and these are the steps which are required for carrying the let's say, or to solve a balance type of fault. So these are the steps involved whenever a network is exposed to a balanced type of fault. So these steps need to be carried to examine the parameters that are the bus voltages and the currents flowing during the fault. So these are the steps, and we talked about the analysis of the balance fault using Thevenin theorem. So we talked about the balanced faults, and today we will start our discussion with the unbalanced faults. So let me now start the discussion on the unbalanced faults. So as I even mentioned that I will be mostly talking about the symmetrical components today, which is one of the method of analyzing an unbalanced fault. So let's start the contents of today's lecture. So first of all, why symmetrical components? So except for the balanced three-phase fault, faults result in an unbalanced system, and that's what we discussed even in the last lecture, that except the three-phase balance fault, because all the three phases are equally affected, so we carry the analysis using a single phase. But that class of the faults is quite rare. Although it's the most severe type, but the probability is quite low. And the unbalanced faults in general are the most frequent types, among which the single line to ground fault have the maximum probability or the maximum appearance. Except for the unbalanced three-phase fault, faults result in an unbalanced system. The most common types of faults are single line to ground and line to line. Other types are double line to ground, could be even an open conductor, and balanced three-phase faults. The easiest method to analyze unbalanced system operation due to faults is through the use of symmetrical components. As I have discussed in the last lecture, that we analyze the balanced faults using Thevenin theorem, and we even solved a problem using the Thevenin theorem to analyze the bus voltages and currents flowing in a network using the Thevenin theorem. But to analyze unbalanced faults, we use the method of symmetrical components. That's why we need them. So unbalanced faults are analyzed using symmetrical components. So we will be talking about the symmetrical components in this particular lecture. So let me proceed. Symmetrical components. The key idea of symmetrical component analysis is to decompose the system. For instance, the phase quantities such as currents and voltages into three sequence of balanced networks. So we decompose the phase quantities, for instance, current or voltage, into three sequence of balanced networks. I will discuss that later on, why we call them balanced or how they are balanced. So, but anyhow, the phase quantities, they are decomposed into three sequence of balanced networks. We will have three set of balanced quantities. The networks are then coupled only at the point of unbalance. So those networks will be solved separately, and then they are combined to get the result at the point of unbalance, that is the fault point. The three sequence networks are known as the positive sequence, you are well aware of that, negative sequence, and a zero sequence. So when we decompose the phase quantities into symmetrical components, we get these sequences. So once again, the unbalanced faults, they are analyzed using the symmetrical components. And what are symmetrical components? Symmetrical components are basically when we decompose the phase quantities, for instance voltage and current, into three sequence of balanced networks. So now let me demonstrate or show these concepts to you with the help of these features. Let's say this is a network having some generators and then transformers and then some bus bars. Let us assume that an unbalanced fault appear on one of the line, resulting in the let's say or it result in the unbalanced system. So when, let's say, an unbalanced fault appears, the system will become unbalanced, and obviously then these quantities, if one look here, the resultant currents, one can even talk about the voltage or the currents. So if one look here, these three quantities, they are no more balanced, because we know about the balanced system where the magnitude of the quantities are equal. They are phase shifted by 120 degree and their magnitudes are equal. But if one look here, once unbalanced fault appears, then the magnitude of the quantities are no more equal. So this is basically an unbalanced situation where the three phases have different currents. So what we do afterwards, we decompose these quantities using symmetrical transformation, that what we will learn later on. So using the transformation, these quantities, these three phase quantities having different magnitudes, through the transformation, they are converted into balanced systems, and those systems or those quantities that we will get after the transformation are known as zero sequence, positive sequence, and a negative sequence. So here we have, once we transform the phase quantities into the symmetrical components, we get the sequence networks. And these are the three sequence networks. One is called zero sequence. This is the positive sequence, and that is the negative sequence. I will talk about these sequence components in more detail when we proceed with the lecture. So, the idea here is that unbalanced quantities through transformation are converted into balanced quantities. And these are basically the resultant quantities, which we get as a result of the transformation. So unbalanced quantities through transformation are converted into balanced quantities, what we call basically zero sequence, positive, and a negative sequence. So let me explain here. As I mentioned, that these quantities are balanced because if one look here, the zero sequence quantities have equal magnitude and they are in phase. The definition of the balanced system, we have discussed this concept before, where the quantities have equal magnitude, phase shifted by 120 degree. So if one look here, the zero sequence, they have equal magnitude and all are in phase. The positive sequence quantity have exactly, equal magnitude and phase shifted by 120 degree. Similar is the case of the negative sequence quantities. They have equal magnitude. Although it is important to mention here that the magnitude of the, let's say, quantity in zero sequence, positive and negative sequence is not the same. These quantities may have different magnitude than the positive sequence quantities. But all the three quantities in the negative sequence, or these components, have equal magnitude phase shifted by 120 degree. Although their magnitude could be different than the positive sequence quantities. And similar is the case of the zero sequence quantities. But in one sequence, all the three components have equal magnitude and phase shifted by 120 degree. In case of the zero sequence, they have equal magnitude and in phase. So that's why after decomposing the symmetrical component using transformation into these three set of components, these are balanced quantities. And these are known as sequence quantities or sequence components. So let me talk about these quantities now a bit more in detail, that how we can get the sequence components from phase quantities. So we will talk about that now, that we need to decompose these phase quantities into the sequence quantities. But what we need for that we will discuss now. So let's say these are three phase voltages: phase A voltage, phase B, and phase C voltage. They are decomposed into three set of components. One is called zero sequence, one is called positive sequence, one is called negative sequence. You know that in a positive sequence, the quantity, what we basically call, let's say the phase A, it is followed by phase B, and then phase B is followed by phase C. In a negative sequence, phase A is followed by phase C, and then phase C is followed by phase B. That's what we call negative sequence. We are all very well familiar with the positive sequence. So once again, as I mentioned, that in each sequence, the magnitude of the quantities are the same. Although they could be different than the magnitude of the quantities in the other sequence. So in the zero sequence, the magnitude of the quantities are the same and they are in phase. Similarly, in the positive sequence, phase A is followed by phase B, and then we have phase C. they have all equal magnitude and phase shifted by 120 degree. In the case of the negative sequence components, phase A is followed by phase C, and then we have phase B. All these are once again phase shifted by 120 degree. So in order to decompose the phase quantities into sequence quantities, we need an operator. So if we have unbalanced net currents or voltages that are required to be decomposed into the sequence quantities, we need a transformation. So now we will talk about the transformation. How to decompose phase quantities into the sequence quantities. For that we need a transformation, and now we will discuss about that transformation. So it's mentioned here that we need a vector A, which is basically put as one angle 120 degree, called an operator. We call A as an operator, and when any phasor is multiplied with A, that phasor rotate by 120 degree anti-clockwise. We are talking about the decomposition of the phase quantities into the sequence quantities, and for that we now are talking how we will decompose that. So for that we need an operator A, which we put equal to having a magnitude of 1, an angle of 120. Obviously when it is multiplied with any phasor, then the resultant will be the phasor quantity that will be shifted by 120 degree anti-clockwise. So now let me talk about the quantities. Let's say, as I mentioned even before, that if we have unbalanced currents, we decompose them into 3 sets of equal quantities, and those sets are called 0, positive and negative sequence components. So let's say we have an unbalanced fault where the phase quantities are no more have equal magnitudes, as one can see here. Phase A have a vector that is shown here, and then we have phase B here with a much smaller magnitude than phase A, and similarly we have phase C here. This is positive sequence where A is followed by B and B is followed by C. So this is now an unbalanced situation where the phase quantities, they have different magnitudes. So now after the transformation, we get a 0 sequence components, a positive sequence components, and a negative sequence components. As one can see here, in the positive sequence, A is followed by B and B is followed by C. In a negative sequence, we have A phase followed by C, and then we have phase B. So these quantities through transformation are converted into or decomposed into 3 sets of equal quantities. This is the 0 sequence quantity, this is the positive sequence quantity, and this is the negative sequence quantity. So it means that each phase quantity here will be decomposed into 3 components. So now if we add the 0 sequence, the positive sequence, and the negative sequence, or the 0, positive and negative sequence component of each phase, we will get the resultant phase. So it means that each phase quantity can be decomposed into 3 sequence components: 0 sequence, positive sequence, and a negative sequence. So now let me show you that this situation can be equivalently represented or equivalently shown here, where each phase quantity is decomposed into 3 quantities: a 0 sequence component, a positive sequence component, and a negative sequence component. How to get it, I will talk about that later on. So if I look here, phase A in this have this particular direction, and this can be decomposed into 3 quantities. So now this is the 0 sequence quantity, that is the positive sequence quantity, and that is the negative sequence quantity. And let's say because they are in phase, so now phase A voltage, which exactly is in parallel to this one, have three components. As if one look here, we can draw parallel phasor to this one to represent the zero sequence component. Then we add to that the positive sequence component, which is in parallel to this component, and then the negative sequence component is this one. If one look here, so zero sequence, positive sequence, negative sequence, they are all added together. This is zero, this is positive, that's a negative. This is parallel to this one. The positive is parallel to, obviously, to this one. One can look here, and the negative one is parallel to this one. So the three are added to get the phase quantity, and similar is the case of the other two phase quantities. So each phase quantity, whether current or voltage, can be converted into three sequence components. How to get those sequence components? Now I will talk about that. And as I mentioned, that for transformation we need a vector A. We need a vector A having a magnitude of 1 and an angle of 120 degree. We call it an operator. Whenever it is multiplied with any phasor, it is shifted anticlockwise by 120 degree. So now let me talk about some common identities involving the operator A. So the operator A having a magnitude of 1 and an angle of 120 degree can also be written in the rectangular forms like that. These are the rectangular components, equal to half plus j under root 3 divided by 2. A square, as we know that this quantity 1 angle 120 can also be written like ej 120. This is the exponential form. So if it is multiplied by a square, we know that this will become 240, which is shown here. And if it is multiplied by 3, power of 3, that will become 360. So now A square will be equal to 1 with a magnitude of 240, and we know that 240 is also equal to minus 120. So this will now be the conjugate. A square is the conjugate of A, because now the angle is opposite to this one. So when the angle change, when it is with the negative sign, then obviously this will also become negative, because this is the cause of the negative angle, this is the sign of the negative angle, and the cause of the negative angle, we know that cause of the negative is still, because this can also be written as cos of theta plus j sine of theta. In this case it is 120, so whether it is 120 or it is minus 120, the magnitude will be the same, because cos of the negative angle is the same as cos of the positive angle. But in case of the sine, when the angle become negative, the magnitude will become, the positive sign will become negative here. So if you put 120 or minus 120, obviously if it is in case of 120, it is half and then minus 1 by 2 plus j under root 3 divided by 2. Even if you put minus 120 degree angle, then it will be minus 1 by 2 minus j under root 3 divided by 2, which is the conjugate of A. So A square is the conjugate of A. A cube or A power 3 with an now, as I mentioned, if we put a 3 here, it will become 360. So this is the same as 1 angle 0, which is 1. So now 1, these are some identities I am talking about, that, and that we will see when we will talk about the transformation matrix. So we will discuss that later on. So 1 plus A square will be equal to, obviously this is 1, and we put in for the A these two components, which is minus 1 by 2 plus j under root 3 divided by 2, and for A square, which I mentioned that now it will be minus 1 by 2 minus j under root 3 divided by 2. So if we now add these quantities, the resultant is 0. So the sum of 1 plus A square is 0. Also JA will be equal to, because we know J is equal to 1 angle 90. So JA will be equal to 1 with an angle of 210. So now from this particular expression, one can write that 1 plus a will be equal to minus a square, and that is also equal to 1 angle 60 degree minus a square. Similarly, 1 plus a square is equal to minus a, and that is equal to 1 angle minus 60. Similarly, 1 plus a square is equal to minus 1, which is also equal to 1 angle 180. So these are basically some common identities that will be used later on when we will analyze the networks exposed to unbalanced faults. So to get the quantities or to get the information about the current and the voltages, these identities will be used. So now with the help of this operator and with the help of these identities, let me now talk about the other quantities, and then we will also get a transformation matrix, how to convert phase quantities into sequence components or symmetrical components. So let's say we have the positive sequence where a quantity VA1 that we already talked about here. This is VA1. This is the the positive sequence representing the phase A. This is phase B, and that is phase C. So for a positive sequence, let's say we call VA1, and as one can see here is the angle. The angle is 0 here. So let's say we call VA1, or we represent it in the phasor form as with VA1 magnitude and angle of 0. We call it, let's say, V1. So we called this quantity, this particular quantity, we called it, let's say, V1. And as I mentioned that if you want, let's say, to rotate this quantity by 120 degree, what we need to do? We need to multiply it with operator A. So as one can see here that if we multiply this quantity with an angle of 120, we will get anti-clockwise this quantity. So if I multiply VA1 with operator A, which one can look here, we call basically VA1, as one can see here, V1. So if I multiply it with A, I will get the VC1, which represent in the positive sequence phase C. And if I multiply it with A square, so that will be shifted by 240 degree, and 240 is obviously also equal to minus 120. So that's what I said, that when a vector is multiplied by the operator A, that is anti-clockwise shifted by 120 degree. And in this particular case, as one can see here, that when this quantity is multiplied by A, this is the resultant quantity, and if it is multiplied by A square, that will be the resultant quantity, because A square is angle of 240. We discussed that before. That is 240, also equal to minus 120. So now, as I mentioned, that let's say VA1, which is this quantity, we call it V1. Then VB1 will be equal to VA1 with, when I multiply with A square, that is here, because VB1 have equal magnitude but phase shifted by an angle of 240 in the anti-clockwise direction. So that will be equal to A square V1, because both have the same magnitude, but this represents the phase shift of the V1 with an angle of 240. And similar in the case of the C1, it is 120, as in the positive sequence A is followed by B and B is followed by C. So this is positive sequence. So now for the positive sequence, we call VA1, and as it is taken as a reference, so it has an angle 0. This quantity have an angle of 240 and this quantity have an angle of 120. So with the operator, now looks like that. V1 A square V1, because VB1 is with an angle of 240 and VC1 is phase shifted by 120, so that is now AV1. So now correspondingly for the negative sequence, if one look here, let's say we call VB VA2. This is the case of the negative sequence where A phase is followed by phase C and phase C is followed by phase B. So now here will be 120 degree and this will be 240. So we call VA2 as V2. So now let's say VA2, which is lying on 0 angle, we call it V2. So now, as I mentioned that all these sequence components have equal magnitudes. Here, the magnitudes are the same, they are only phase shifted. Here we call the magnitude as V2, and then they are phase shifted by some angles. So among each sequence, the magnitude of the three components are the same. That's why they are called balanced components. So now we are talking about the negative sequence. So VA2 with an angle of 0, we call it V2. Then VB2 will exactly have the same magnitude but phase shifted by 120 degree, which means that we need to multiply A with V2. So A, as one can see here, this is 120. So if you multiply A with V2, it will become V2. And if you multiply A square with V2, so that will be shifted here. So this is VC2. So as one can see here, VC2 is A square V2. I hope now this is quite clear to you. A is an operator which have a magnitude of 1 and an angle of 120, and whenever a vector is multiplied with A, it is shifted by 120 degree. And now I have discussed the positive and negative sequence with the help of the this operator, that how one can write. If let's say we call this vector as V1, so how one can write VC1 and VB1 and similarly for the negative sequence. So we have discussed that now here. Now zero sequence, as all the three are in phase, so VA0 will be equal to VB0 and VC0. They have equal magnitudes. We call them V, or we represent them with V0. So they are in phase. We don't need here the vector, the operator A. So zero sequence have equal magnitude and they are in phase. They are not phase shifted. They are in phase quantities with equal magnitude. Once again, the magnitude of the components here are equal, they are phase shifted. Here the magnitudes are equal, we represent them with a different symbol, but they are phase shifted. Here we have a different symbol. So all these three components will have same magnitude. Here also have same magnitude, only phase shifted. Here also same case. So now let's say we call V0, V1 and V2 as the 0, negative and positive sequence of phase A. These are now, as I mentioned, if one let's say, let me now once again talk about this particular case. As I mentioned before, that each phase quantity can be decomposed into three components. VA0, what we now represent in this particular case is V0, VA1, what we called V1, and VA2, what we represent with V2. So now this will be the 0, this is the negative, and this is the positive sequence component of phase A voltage. I hope now this should be clear to you. So let me proceed now. So then one can write that phase A have three sequence components: zero sequence, positive and negative. Similarly, phase B have three components. Phase B voltage have three components. One is the zero sequence component, one is the positive sequence component, one is the negative sequence component. So now they can be written as here. VB is, this is the zero sequence component, this is the positive sequence component, and this is the negative sequence components. And just if we take it from the, I mean, if we look here, VB1 is equal to A square V1. So we put here as A square V1, and then VB2 is equal to AV2. So that we put here. Similarly, in the case of the VC, the phase C voltage, it has a zero sequence component, positive and negative. Now VC1 equals AV1, that we put here, and VC2 equal to A square V2. Now it means that these three phase quantities have been decomposed into zero, positive and negative sequence quantities. So these are the phase quantities, and V0, V1 and V2 are the sequence components. So now this situation can also be written in the matrix, or this expression can be written in the matrix form. So these are the phase quantities, these are the sequence components, and this is what we call transformation matrix. As I mentioned before, that in the case of the unbalanced faults, where these magnitudes are no more equal, with the help of this transformation matrix, we can convert the phase quantities into the sequence components, because we know A square, A, and this is an operator. If we know the phase quantities, we can get the sequence components. And as I mentioned, sequence components, whether it's a zero or it's a positive or it's a negative, all sequence components, for a zero sequence the magnitudes are equal, they are in phase. For the positive sequence, once again, the magnitude of the positive sequence voltage is, or current, is the same, only the other quantities are phase shifted by 120 degree. And similar is the case of the phase C quantities. So now we are writing the phase voltages as a product of the transformation matrix and the sequence component. So let's say we represent this matrix with V and P. V is the voltage, P is the phase. This is the transformation matrix. This we call them A, and these are the sequence components. So we call them, we represent them with V subscript S. So the subscript P here represent the phase quantities, and the subscript S here represent the sequence quantities. If we want, if let's say the phase, phase quantities are given, we can get the sequence components by taking the inverse of the matrix. And if the sequence components are given, one can even get the phase quantities. So I mean, one can solve this problem either way. So the inverse of the matrix is equal to this one. You are, I mean, familiar with getting the inverse of a particular matrix. So now these are the phase quantities, this is transformation matrix, these are the sequence components. And if let's say we want to get the sequence components from the phase components, this will now be the situation where we need the inverse of the matrix. So that is the inverse of the matrix, and these are the phase components or the phase quantities, these are the sequence components. So as I mentioned before, that for analyzing the unbalanced faults, we need to get the symmetrical components. And now I have talked about how to let's say achieve the symmetrical components when the phase quantities are given. So let me find that yeah, here it is given. As I mentioned that if let's say there is a fault, then the phase quantities will no more be balanced, and using transformation we have to convert them into three sequence quantities: zero sequence, positive sequence, and negative sequence. It is shown here. Zero sequence quantities equal in magnitude, in phase. Positive sequence quantities equal in magnitude, phase shifted by 120 degree. And similarly the negative sequence equal magnitude. Although once again these magnitude of the negative sequence components may be different than the positive sequence components, but here all the three components, they are equal in magnitude and phase shifted by 120 degree. That's why each of them are called balanced quantities. This is a balanced system where the magnitude are equal in magnitude. I mean here the equal magnitude and phase quantities. Equal magnitude phase shifted by 120 degree. Equal magnitude phase shifted by 120 degree. So that's why they are balanced. This is not balanced. This is an unbalanced system. So in other words, we are converting with the help of transformation and unbalanced quantities into balanced components. So we talked about the voltage here. I mean the case will be the same if we talk about the, let's say, the current. So now after this one, I mean if one look here, these are the sequence components, these are the phase components or the phase quantities. So now we can write here one V naught, which will be equal to VA plus VB plus VC divided by 3. So that is equal to, so V naught, which is the zero sequence voltage, will be equal to 1 over 3 VA plus VB plus VC, and similarly one can write V1 and V2. So they are given here. Now for a balanced three-phase system, if the system is balanced, then one can look here, as we know that if the system is balanced, it means that it will either have a positive sequence or a negative sequence, because when the system becomes unbalanced, then the sequence component appears. But if the system is balanced, so one can see here for a balanced three-phase system, V naught, where this is VA plus VB plus VC. If we add all these three phase quantities, they are phase shifted by 120 degree, and we know that if we add three phasors, if they are phase shifted by 120 degree, then the sum of those three phasors will be equal to 0. So that's why a balanced three-phase system have a 0 sequence voltages. In unbalanced three-phase system, line to neutral voltages may have 0 sequence component. So if the system is unbalanced, they may have the 0 sequence component, but in an unbalanced system, in a balanced system, the 0 sequence component is 0. But in an unbalanced system, there could be 0 sequence component. The symmetrical component transformation can also be applied to currents. Obviously, the same discussion, the same transformation that we have now already discussed, that whether it's a voltage or it's a current. The phase quantity, if one look here, the phase quantities are equal to transformation matrix and the sequence components. Here is exactly the same case. The phase current is equal to the transformation matrix and the sequence currents. And if one want to get the sequence component from the phase component, we need to multiply the phase quantities with the inverse of the transformation matrix. So same is here. So whether it's a voltage or it's a current, the appearance of the expression is the same. So phase component of the current is equal to transformation matrix and sequence component of current. Sequence component of current equal to, obviously we have to take the inverse of the matrix. So if we want to get it, the sequence components of the current, one has to take the inverse of the matrix. So that is the case. The phase currents are, as I mentioned before, if one can write the phase A voltage as 0 sequence plus positive sequence plus negative sequence. The same is the case here. Phase A current equal to 0 sequence current, positive sequence current, negative sequence current. And similar is the case for the other two phases. Likewise, we discussed about the phase voltages. They can be written as, sum of the sequence components and the multiplication of the either the vector A or the square of the operator A. So the same is the case here. Exactly the same case. IB equals, which is the phase B current, equal to 0 sequence component square of the positive sequence, and then the operator A and negative sequence, Similar is the case for the phase C current. So let me now also in a same manner that what we wrote here, 0 sequence voltage equal to 1 over 3 phase A voltage plus phase B voltage plus phase C voltage, or phasor A plus phasor B plus phasor C. So the same is the case here. 0 sequence current equal to 1 over 3 phase A current, phasor obviously, plus the phasor B, the phase B current and the phase C current. Same is the case for the other two phases, for the other two sequence components. So in a Y connected three phase system, here once again I mean to mention here that in a balanced system the zero sequence component of the voltage was 0, but in an unbalanced system there could be, we will later on solve problems, you will see that if a system is unbalanced there could be even all the three components or all the three sequence components, but in a balanced system we could either have positive or could have negative. If the sequence is, if let's say we have positive sequence, then only positive sequence will be existing, neither zero sequence voltage, neither negative sequence voltage. If we have a zero, if we have a negative sequence, like if the system is, let's say, in such a way, designed in such a way that after phase A we have phase B and then the phase C, so then it's a negative sequence, then obviously we will have only negative sequence voltage. These two will be 0. But in an unbalanced system, all the three sequence voltages and correspondingly the currents may have certain values. So in a Y connected three phase system, as we know that the neutral, the current flowing in the neutral line equal to the sum of the three phase currents, which is equal to, if one look here, IA plus IB plus IC, if one multiply 3 on that side, it will become 3 I naught. So from this expression, the current flowing in the neutral line is equal to 3 I naught. I naught is the zero sequence current. So in a balanced three phase system, once again in a balanced system, if you remember, we have discussed this point even before, that in a balanced three phase system the current flowing in a neutral line is 0. So if the current flowing in a neutral line is 0, it means that I naught is 0, which is the zero sequence current. So line currents have no zero sequence components. Also in three phase system with no neutral path, for example delta connected system or Y connected with ungrounded neutral. So even in a Y connected load or Y connected, let's say, source generator, if there is no, if the neutral is not grounded, line currents may have no zero sequence component. If it is either delta connected or Y connected but neutral is not grounded, then in that case also the line current may have no zero sequence component. Obviously in the case of the balanced system, when the neutral is grounded, even in that case the zero sequence component is current, zero sequence current is zero sequence current have zero value. But if let's say we have a three phase system where there is no neutral path, for instance delta connected system or Y connected system with ungrounded neutral, the line current may in that case also have no zero sequence component of the current. So now with this discussion I conclude this lecture, and let me summarize the lecture. We discussed that if let's say an unbalanced fault appear, then the phase quantities may have different magnitudes. As one can see, it's not a balanced system anymore, where the magnitude of the current in each phase is different. But this unbalanced system through transformation, what we have discussed now, can be converted into balanced system, and we in the result get three sequence components: zero sequence component, positive sequence component and negative sequence components. So now we have talked about the symmetrical components, and we have even talked about the transformation of the phase components, the unbalanced quantities, into the three set of what we call the three sets of the sequence components. So with this now I end this lecture, and in the next lecture what we have now discussed theoretically, I will try to solve some problems to make the understanding of the the conversion of phase quantities into sequence quantities more clear to you. So we will use this particular expression or this transformation to get to convert phase quantities into sequence component and sequence into the phase components. So now with this discussion I end this lecture, and in the next lecture inshallah I will solve some problems to make the theoretical understanding more clear to you. So thank you very much for your attention, and see you inshallah in the next recorded lecture. Thank you very much once again. Assalamu alaikum wa rahmatullahi wa barakatuh.